a rational function, and we don't know what this one looks like. Notice that the other two examples, we had a pretty good idea of what they looked like already, right? I mean, you knew the cubic had that shape to it, and the other one, you're like, oh, it's up and down here. This one's a little bit different. Tell me something, anything about it, just by looking at it.
It's gonna have a symptom.
Okay, asymptote, vertical asymptote probably where?
One.
One and,
Negative one.
yeah, so vertical asymptote's at x equals positive 1 and negative 1. Okay?
Horizontal at 2.
Yes, horizontal at 2. So what Aiden sees here, and I want to be clear, is that a quick way to be able to examine rational functions is if you just take 2x squared over x squared like we did yesterday, you get 2, right? So the horizontal asymptote is going to be y equals 2. Yeah.
So say that it was 2x squared on the top and it was just x on the bottom.
Yeah, so that's what I want to talk about. Suppose you had 2x squared over x. The fact is that it's not going to have a horizontal asymptote. It's going to look like then 2x. It's going to look like a line with a slope of 2.
Okay.
Do you know what I mean? Suppose it was 2x cubed over x. Then it's going to head off like a parabola at the very end. You know what I mean? So if you just divide those larger terms, you can see. If you do it the other way, if you have 2x over x squared, notice how the denominator is larger? Because the denominator is larger, it's just going to go to 0. It's just going to flatten out on the x-axis then. So the bottom wins out. You know what I mean? Here the top wins out, you get 2x. Here the bottom wins out, and you get 0. If they're the same degree, then in this case we have 2. Is everybody okay with that? All right, how about the x-intercept? The x-intercept happens when the y value is equal to 0. So if we set this equal to 0, is a fraction equal to 0 when the top is 0 or when the bottom is 0?
Top is 0.
Top is 0, and obviously that happens at 0. To find the y-intercept, you plug in 0 for x, and notice you would get 0 over negative 1. So you can see that this does go through the origin. Any questions? To get the rest of the information, you have to know calculus. What is the next step in this process?
Take the derivative.
Derivative. Here we go. I've got f prime of x is equal to, and on your test, I need to see your derivative tests. I need to see you show the derivative. So the derivative of 2x squared is, or x times the x squared minus 1. Minus 2x squared times 2x. All over x squared minus 1, quantity squared. Okay. So I get a 4x cubed minus 4x minus 4x cubed over x squared minus 1 quantity squared. Or negative 4x over x squared minus 1 squared. You okay with that? All right. So there are 3 points that we're going to have to plot on our number line. What are they?
0. Negative 1.
But we can be a little bit intentional about how we plug these values in, because the denominator will always be positive. Everybody see that? It gives, yes.
Where'd you get that negative 1?
So the denominator is equal to 0 at positive 1 and negative 1 because of the x squared minus 1.
Oh,
Okay. So as I plug in negative 2, negative 4 times negative 2 is positive 8. And we know the bottom is always positive. So you get a positive value here. And as you plug in negative 1/2, you're going to end up with a positive. And obviously now if you plug in positive values, you're going to come out with negative. What does that tell me? Good. So I've got increasing happens from negative infinity to negative 1, union, negative 1 to 0.
I wrote that down right.
Are you sure?
Yeah.
And decreasing from 0 to 1, union, 1 to infinity. Does it have a local minimum?
No,
No. Why?
because it doesn't change from negative to positive.
Doesn't change from negative to positive. Does it have a local maximum?
Yes.
Where?
0.
We know if we plug in 0, we get 0. We know it goes to the origin. Turns out at the origin there is a local maximum. Okay? So we know that. Just because it changes sign, though, we have to make sure that it's part of the domain. So is 0 part of our original domain? It is. What if it changed at negative 1 or 1? Then we would not include those because they're not part of the original domain. Are we clear about that piece? Then we move on. Now what? Second derivative. F double prime of x. And even though I've done this a lot, every time I see a second derivative of this order, I'm like, gotta be careful here. I mean, there's lots of rooms for errors in the second derivative, isn't there? So derivative of the top is negative 4 times x minus 1 squared.
X squared.
X squared minus
X, thank you. Minus, what the top is negative 4x, right? So I could write plus 4x times the derivative of the bottom. How will we do the derivative of the bottom? Chain rule. So I have u squared, I have x squared minus 1, 2x and 2u. It looks like a 4x times x squared minus 1. So times another 4x times x squared minus 1. All over? Good. So again, our goal is to be able to find the critical values. I have 3 terms, the one in red, the one in blue, and the one in green. So terms are things that are separated by our addition and subtraction. They all have what common factor?
X squared minus 1.
They all have at least one x squared minus 1. Agreed? So I can divide out an x squared minus 1 with the top and the bottom. As I divide that out, that will go away. This will reduce to 1, and this will reduce to 3. Then I'm left with negative 4x squared. So I distribute this. Plus 4. Plus what? 16x squared. All over.
X squared minus 1.
X squared minus 1 cubed. We end up with a 12x squared plus 4 over x squared minus 1 cubed. Is the top ever equal to 0? No. What does that mean?
It's not gonna have any function.
It will not have inflection. Okay? The bottom is equal to 0 at 2 values. I don't need to plot anything at the top, but at the bottom I can plot negative 1 and positive 1. Tell me something else about the top. It is always positive. So before the denominator was positive, here we know the numerator will always be positive. So as we plug in values, we can know that the top is always positive. I plug in negative 2. Negative 2 squared is 4, minus 1 is 3, 3 cubed is positive. So this will be positive. I plug in 0. Will that give me a positive or a negative? It will give me a negative. And if I plug in a value to the right of 1, I will get a positive. Everybody okay with those? All right, let's sketch the graph and be done. What we know about this is that it has no inflection because although it changes sign at -1 and 1, those are not part of the domain. So we, yes, but we will write the concave up and concave down. So inflection is gone, but concave up is going to be from -infinity to -1, union 1 to infinity, and it's concave down from -1 to 1. It's time to sort this out. We don't know exactly what it looks like, so we're gonna make our graph. I'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yesterday, I don't feel like I did a very good job of graphing that cubic. I'm going to try harder here. I have vertical asymptotes at positive and -1. And I have a horizontal asymptote at +2. What is the only coordinate that I'm ready to plot?
0, 0.
Yeah, it happens to be my intercepts as well as the local maximum. Now we're going to use some information here. Does it start concave up or concave down? It starts concave up. And does it start by increasing or decreasing? So the only way to draw the graph over here is to draw it like this to show it's concave up and it's increasing. Careful to my words. After that, am I increasing or decreasing? You are increasing after that. Notice how it continues to increase. And then, are we concave up or concave down after that? It is concave down, but it is increasing. So I'm increasing, but I'm concave down. And then it is decreasing immediately after that. After that, it continues to decrease, and then it is concave up. So the only way to draw decreasing and concave up is on this side to do that. So once again, you can see Isaac Newton sitting there without a calculator. How does he perform these type of operations? He could get a very clear picture of what this looks like. We didn't really have any idea of what it looked like, but we are going to quick just check it on our calculator. And so I go to my TI-84. I'm going to open that up. Oops, there was a problem, it says. College algebra kids just had their logarithm test, and now they are moving on to their word problems. We'll see what kind of responses we get. I'm going to clear that out, go into our y equals, and then the top we have a 2x squared divided by, and in the bottom I'm going to put x squared minus 1. Again, I'm not allowing you to press graph when you get to this test, but we are doing it right now so we can check and see what kind of a job we did.
Wow.
I'm going to zoom standard so I could get a more of a 10 by 10 window. How do you feel like that compares to our drawing right there?
I think it's pretty spot on.
Yeah, I think, I'm going 9.5 on that. Well, that's pretty impressive. And if you want to tighten any of it up, you can go ahead and just, punch in values and try to get a couple coordinates here or there. But that's pretty good. So, when people feel like often they're like, well, we're just kind of estimating graphs. No, not at all. Remember last year when we graphed sine and cosine and secant had those U shapes and tangent and stuff? They're like, oh, it kind of feels like you're just making scribbles. When really at the end of the day, those were really accurate graphs. We are also able to produce incredibly accurate graphs.
Well, why would you need to do this? Or like, why would you need to know what this looks like?
It's a good question.
Like, isn't the table always kind of like your best friend? Because you know what the exact values are. You're wondering like when it's, certain stuff. Or like, why would you want to see it?